Good morning. So the last class actually you visited the holography lab, right? So what did you see there? What holograms did you see? Okay. Was the setup to record also there or only holograms were there? Okay. Okay. And did he show you if with the broken plate that he was still able to reconstruct the full? Okay. Okay. So I hope the visit brings it, because the equations do only so much, but when you see it, you now one thing is when I started the topic, one of the reasons I said it was important was it is, for example, used to make security features, because making an image of something is easy, whereas making a hologram of something is, of course, you need to have the technical expertise to do it, and it's much harder to do, and that's why many companies will make their stickers with that and use that as in order to show that the product is genuine, comes actually from that company. But what you can do with holography is not limited to only having some genuine, this is a true brand feature, but you can do a lot of different kinds of measurement on a lot of different experiments which allow you to get information. So it's a very powerful sensing technique. So it's such a vast area, you could really spend an entire semester talking about holography. But of course, we don't even have much of a semester left. So I just want to show you one application of holography today. So this is what is shown here is the setup where we are doing the reconstruction alone. So you have the previously recorded hologram, and then it's illuminated with the reference beam, which ideally should be equivalent to the original reference beam, and then you will create two images, one virtual, one real, but these are now 3D images carrying the depth information. A way to extend this idea is to do what is called holographic interferometry. Now you know holography itself is an interferometric technique. You are recording phase, or you are capturing that phase information because of the interference of the scattered object wave with the reference wave, right? But here we are now doing going a step further. So in holographic interferometry, what is the goal? You want to make a hologram of some object, the object that you want to study, and you want to see how that object changes over time, how that object changes when you apply some stress to it, how that object changes when it is excited by certain frequencies. So how are you going to do this in real time? You make first a hologram of the undisturbed object, then you put that hologram back into your setup. So now you have two object beams. It's not the reconstruction setup, it's the recording setup, but you have a hologram there. So you have the object beam from the original object, and you have the object beam from the hologram. Now if you disturb the object, you are making a difference in the beam that is coming real time compared to the beam that was recorded, and you will see the interference of these two object beams. Okay, is that clear, or should I run through that one more time? Your goal is to study an object that is not static. Something about that object is changing, and that change could be a variety of course, you understand when I say something is changing that affects the optical path difference, right? So maybe refractive index is changing, path lengths are changing, and how could those changes be? You could be straining the object, you could be heating up the object, you could be exciting it with a certain frequency, a variety of different techniques could be used, or it's not that they are used, the object is experiencing these phenomena and you want to make some measurement of these phenomena. Okay? So, you are putting back, you make a hologram of the undisturbed object, put it back in that original setup. So, the original object beam is still there, and then you are looking at the interference of the original object beam and the undisturbed object beam, and it is the interference of these two that you are looking at. Okay? And this is a very powerful technique because it also allows you to study very large objects. You can expand a beam to very large. Right? We already, when we were looking at Gaussian beams, said people did experiment where they sent a Gaussian beam from here to the moon. Now, while you are not measuring that entire diameter on the moon, you know that you are talking about a very large beam. So, if I want to study an object, now what is a very large object I might want to study? Well, there are objects we want to study because we want to ensure that there is no defect in them. Okay? An aeroplane wing, we need to quickly assess, is there a crack in this aeroplane wing? Now, I could take a small sensor and go millimeter by millimeter and scan over that and see, am I getting a crack? Is there some way to look at that aeroplane wing at one shot and figure out if there is a crack somewhere? So, can fringes give me that information? So, holographic interferometry is used in examples like that. So, let us look at this example. I think I showed you this somewhere in the beginning of the course. In this example, this picture has been taken using holographic interferometry. What are they doing? They are exciting the different modes of this musical instrument. So, they had a hologram where the musical instrument is undisturbed, and then they put that hologram back into the setup. There is the beam reflecting off the vena. You excite some string of the vena, so there is certain resonance that is happening. That object beam is interfering with the original undisturbed object beam, and what you are seeing is the interference pattern. And so, for every mode that the vena has, you will see a different set of fringes. Right? So, it is a way of studying the modes of this musical instrument. Right? This was work done in the physics department of IIT Madras. But I could say, like I said, I want to study an aeroplane wing. Maybe I set it into vibration, or in the case of the aeroplane wing, maybe I just look at the fringes across the entire wing. Wherever there is a defect, the fringes will have some kind of abnormal look to it. So, you can immediately tell there is something wrong at this place. Then you can take a smaller sensor and study that localized area, and that will quickly tell you if there is a problem or not. Whereas, if you took a photograph of the wing, you would not be able to tell. From the photograph, externally everything may look okay. There may be a small crack under the paint. Right? The reflection from that will carry that information, whereas a photograph of that will not carry that information. Okay. So, holographic interferometry is used in a very, very wide range. Right? I have just talked about the aeroplane wing as one example. I have shown you modes of a musical instrument as another, but there is really no limit to what you could study. Okay. So, we have been looking at, once we started wave optics, we looked at interference, and then we went into some applications of interference, and that is where we started looking at holography. But I want to look at some overall applications of interference itself, not just limited to holography. So, here is a picture of an aeroplane, and you can see a pattern or something over here. What are these patterns that you see here on the windows of this plane? Sorry? So, the patterns are thin film. So, you are seeing, because of some film, some layer on the window, you are able to see these colored patterns. knowing what you now know about interference, can you think of why we see these different colors like this? What if I were to consider this experimentally, what is happening? You're standing outside of this aeroplane looking at this window. So the external ambient light, sunlight, is falling on the window, falling everywhere. And in fact, you see the aeroplane because of the light reflected off this entire aeroplane or whatever part of it, and is coming to your eye, right? Or it has been taken by a camera, so through the lens of the camera. In many parts of the aeroplane, so in all these regions, you just see the plane as you expect to see it. But in these regions, the transparent parts, you're seeing these colored light. So you are seeing these images because of reflection. Reflection is happening everywhere, but something special is happening in these regions. What do you think is happening that is causing these different colors to show up? So what you're seeing is, if I consider that there's a thin layer, so let's say this is the glass of the window and there is some thin film on that. Right? Now it could be that there is some coating on this glass, it could be that it has flown through and it's just landed and it has some kind of, it's picked up some dirt along the way. Right? It could be that they were cleaning it and they haven't finished cleaning it and there's some soapy layer on it still. There is some coating. Okay. To make it easy to understand, let's start with the case where we assume the coating is uniformly thick everywhere. Do you think you would see this then? The fact you're seeing different colors means that it can't be uniformly thick. So you're seeing the image because of reflection. I mean, that's normally how we see anything. The light surrounding, the ambient light reflects off objects and makes it to our eye or makes it to the camera. That's how we see, it's reflection. There's no interference happening there. But in this case, this additional pattern we are seeing, that's not actually, it's not that there is a different color there. The reflected light is interfering with some other reflected light, and therefore what you're seeing is the interference of these beams of reflected light. Okay? So if I consider that you had a uniform film, let's say that thickness is D and let's say the refractive index is N. Okay. Again, just to make it simple, we can start by saying we have normal incidence. That's of course not the case. You would have light coming in at all angles. But let's say we have normal incidence. What is the condition that I have constructive interference in reflection? Can you tell me what is that condition? What's the condition for constructive interference in reflection for a normally incident beam? Sorry, N times D. Okay, so if I'm going to put it in terms of phase, I'll say 2 pi by lambda is equal to, okay. Now you have to be a little careful here. Why? Because what may happen? Yes, so if we assume this is air, this is of course whatever film, and we're saying N has is larger than 1, right? And we have whatever, this is glass, so let's say this is 1.5, right? Whenever there is when you have reflection in a medium which has a lower refractive index than the next medium, you're going to have a pi phase shift. Okay, so in this interface you have a pi phase shift. Okay. Now I cannot say this is the condition for constructive interference unless I know what is n with respect to 1.5, the refractive index of glass. Okay. If n is less than 1.5, that means I will have another phase shift of pi at that interface. So the two phase shifts of pi will cancel out and I have this condition. If, however, n is greater than that of glass, the refractive index of glass, there is no phase shift that happens there. So I have to take into account that additional phase shift of pi, and I'll actually have a odd number of pi instead of 2 pi. Yes, you had a question? No question. Okay. Right? So in this case, since I'm not sure why the film formed, in this case I cannot say what is exactly the condition for interference. What I can say is that it will depend upon the relative refractive indices between these medium. Okay? What I can also clearly say is, wherever I see one color, this means I know this film is not of a uniform thickness. The thickness is varying. In some places, the thickness, let's assume the refractive index is constant. In some places, the thickness satisfies the condition for constructive interference for lambda 1, and in other places for lambda 2. The fact we put this here, 2 pi is a phase change of 2 pi which corresponds to lambda. If I change lambda, it means that is a different condition for that wavelength. So the different colors in this picture here on that part of the plane means that the film thickness is varying, and at different places different wavelengths are satisfying the constructive interference condition, and wherever a particular wavelength satisfies it, you will get that color reflected back. Right? So it's a contour map of thickness. These fringes are a contour map of thickness. Fringes are always like contour maps. But when I have a broad range of wavelengths falling on them, then it's very easily telling me that it's a contour map of the varying thickness. Okay? You can work out the condition if you have the light coming in at an angle, you'll have to take the angle into account. And if you're actually putting a thin film on to some surface, for example, spectacles will often have thin film. When you go to buy spectacles, they may ask you, do you want a thin film coating on it, right? And when you specifically ask for a thin film coating, then the condition is satisfied, so that if this is air, so n air, this is n of the film and this is n of glass, n f is chosen, so n air is of course less than n f, and it's also chosen like this. Okay. So that you have the well-known conditions for constructive interference. Okay. That value of refractive index, this value, in the case of a thin film used, you're using it here for an anti-reflection coating, right? That means you definitely don't want light being reflected back. This simple equation that I've written down here, it tells you something about the thickness. So it's clear you need to choose a particular thickness and of course a film of a particular thickness and a particular refractive index for ensuring that you satisfy this condition. Now, do you think that I can say, I give you a film and I say, here's a film, this is the material we have, and it has refractive index Nm. I give you Nm, right? Do you think that you will definitely be able to cancel the reflected wave? What condition have I not talked about in this? Think about, we are still in the regime of electromagnetics, right? So, you have encountered this kind of thin film or this kind of condition in many other areas of electrical engineering. So, what is the condition over here? You want destructive interference here, not constructive, right? So, you want 2 pi by lambda into Nd to be equal to pi. No, in fact, sorry, that's not even correct. It's not 2 pi by lambda into Nd, because the light is going, there's one beam hitting this surface, there's one beam hitting this surface and reflecting, and then it carries on, and I'm just showing it displaced just to make it easy to see, and comes here. So, the distance that actually has been travelled is 2 Nd. So, there is a 2 here and there is a 2 here. Right. So, for destructive interference, and when I am doing anti-reflection coating, that is what I want destructive interference. This is the condition. That means the thickness D has to be lambda by 4n. Right? So, I am saying for destructive interference, I need a film of quarter lambda thickness. Does this ring any bells, at least for the electrical engineers in this class? You've all done electromagnetics. You've all done. Yes, where did you encounter that? In polarization, but not only connected to light, you see it in other places. So, it says quarter wave plate, yes, but then that's again an optical application. Where else have you seen transmission lines, right? You use a quarter wave transmission line to reduce reflections in transmission lines, right? Don't look so surprised. Are you an electrical engineer or not? No, okay. Then you're forgiven. Do you now remember, the rest of you? No, no idea. So, you meet this condition in several places. So, since you said transmission lines, is that the only condition for the transmission line? Is the length, is the thickness the only condition, or is there some other condition that? What does this lambda by 4 ensure happens between the incident beam and the there are two beams, you want destructive interference to happen. What does that mean? You don't want these to add up. So, the lambda by 4 ensures what? Sorry, say the first part again. So, the lambda by 4 ensures that you are subtracting beam 2 from beam 1. When you subtract 2 beams, is the answer always 0? Depends on the magnitude. This lambda by 4 only ensures you are not doing beam 1 plus beam 2, it is beam 1 minus beam 2. To get anti-reflection, to get no reflection, the result of that subtraction must be 0. How do you ensure that it is 0? The value of that refractive index can't be arbitrary. So, I can't say here is a material, here is its refractive index, now you go choose the right thickness. You can choose the right thickness to ensure there is subtraction. But if you haven't got the right refractive index, you are only reducing the reflection, you are not making it go to 0. And the condition, and this is the same condition that you will have with a transmission line. In a transmission line, you are not talking about refractive index, you are talking about impedances, right. So, in a transmission line, you will say the impedance of that quarter wave plate has to be Z1, Z2 root of, right. where you're inserting this quarter wave transmission line between two transmission lines and you don't want a reflection to come back. And that's exactly the same condition. You say NF must be N air Ng root of. Where's the origin of this? It's not black magic, I'm pulling it out of a hat. What ensures how much light gets reflected? If I want to actually go and solve this, I'll go write out Maxwell's equations. I'll say the wave that is incident has this value, the wave that travels through the film and reflects off the lower surface has this expression. What ensures or what determines how much light is reflected? The boundary conditions. And the boundary conditions in this case are going to be determined by the refractive indices. So, it's the thickness ensures you have destructive interference, but the actual value of the refractive index is going to ensure that you actually make the destructive interference have as low a value, ideally go down to 0. Okay? Both are important. Okay? So, so it's very hard to achieve this, because now I'm saying I need a specific NM, and it's quite hard to achieve this. So, you'll find that in applications where you really need very high levels of anti-reflection, they won't use one single thin layer coating. They'll use a stack, and they'll have N1, N2, N3, N4, and alternating refractive indices will be less than lower, low, high, low, high, low, high, and they will be able to achieve perfect zero reflection from this stack of thin films, not from a single thin film. Okay, there's a whole science to calculating how many films, which refractive indices. They may all be lambda by 4 thickness, but you need to have different refractive indices. Okay, so there's a whole science to that. Okay, is that all? So this pattern, I leave that to you as an exercise to work out what is the condition when you don't have light. I talked about light that's incident normally. What happens if you have light that's incident at an angle? You should see a problem with this, because this means I'm choosing a thickness, and that thickness will work for this angle of incidence. It will not work for another angle of incidence. So, if in an application you know the light is going to be incident at a particular angle, you could calculate the thickness of the film for that angle of incidence. In many cases, they will just do normal incidence, and for normal incidence, you will have the least reflection. For all other angles, you will have some reflection. Right? Or you use the stack to say over a range of angles you are satisfying, so that you get a broader coverage, but you can't do that with a single film. Okay? Yeah, this maybe I just mentioned, I won't go into any detail of it. Hopefully you have all heard of the LIGO. Yes.
Other than just the angle, it will be only for a certain wavelength, right?
That is true. So his question is, when you make a film, you are making a film of a uniform thickness. So you are achieving anti-reflection for one wavelength. But again, with a single layer, that's what you can do. With a stack, you can do, some combination that it will work over a slightly broader range of wavelengths. But with a single film, it will work for one wavelength. You might note, you don't wear glasses, but the people who wear glasses, when you buy and they ask you, do you want a coating, they'll ask you, what color do you want? Because it's anti-reflective, you can choose it's anti-reflective at one wavelength, it will have reflection in another. So you'll see coatings where you pick up the glasses, they have a bluish tinge, or they have a slightly brownish tinge. So it is cutting off the reflection in one wavelength band, the other wavelengths are reflecting and combining and giving you a color. So many spectacles have a faint colored tinge to them.
Because the complementary color is being
exactly. Yes, yes. Okay. So one more application is the LIGO interferometer. You ought to know about this because India is going to be getting a LIGO interferometer. It's a Michelson interferometer, but it has very long lengths of the arms. Okay, so I have been drawing Michelson on this little board here, centimeters length. Does anyone know the length of the arm of the LIGO? Guess? 4 kilometers. So each arm is 4 kilometers long, and the idea is when a gravitational wave passes, it will affect one arm differently from the other, and from that the way it's affected, you will be able to tell something about the gravitational wave. You have to keep they measure differences in distance in the order of 10 to the power minus 18 meters. Okay, 4 kilometer path length, and you're keeping it stable to that accuracy, right? Attometers. So you can see what you're seeing here, it's all enclosed, it's all air conditioned. Right? So you can make very accurate measurements with an interferometer. In order to increase sensitivity, you need to change your path length. Yes, and that's what they're doing with this interferometer here. Okay? But I just wanted to mention it because it just shows you all kinds of things, from the simple coating on your glasses to measuring a gravitational wave or studying defects on a large object, or studying modes of some object that is undergoing vibration. All of this and much more you can do with interferometry or holography, which is a form of interferometry. Okay? Okay. For the rest of the class, I will focus on a different application. So this is work that a master's student of mine had done. So we're going to talk about optical coherence tomography. So when I say tomography, what do you think of? What is tomography? My God, I have to. Sections of image. So you're creating an image, but you're creating slices somehow of that image. So optical coherence tomography is a technique to do exactly that, create sections of an image. It has various uses. Currently now it is used a lot, so we don't need to look at this. It's used a lot in biomedical imaging, but it can also be used in art restoration. You want to look at the different layers in a painting. Earlier, you know how they would do that? If you have an old painting and you want to see the different layers, how would they do that? So when you're doing any study of this kind, when you're trying to get an image, you're doing sensing, you can do destructive sensing, you can do non-destructive sensing. So earlier they would cut out a bit of the film, so of the painting, they would go to a corner and hidden behind the frame and cut off a little bit and use that to study. So that's destructive. Right? OCT is used for imaging of the eye. Now they're not going to say, okay, I need to find out about your eye, let me go in and cut out a little bit and say, oh, you are fine. But no, a hole in your eye now because they cut out a little bit. So clearly when I'm doing medical imaging or medical diagnostics, if I can avoid an invasive technique, yes, we do actually do that. If you suspect a tumor, there will be a surgery, a biopsy to pull out a little bit of tissue to study that. But they're always trying to research ways that you can look at what's happening inside the body without having to physically go inside the body. So you want a non-invasive. Non-invasive when you're talking about humans, and non-destructive when you're talking about some mechanical body. Okay. So OCT is a non-invasive technique, right? We have other non-invasive biomedical imaging techniques. You have ultrasound, right? You have MRI, right? I think I don't have that picture here, but if you look at the resolution, so what's the problem, or why does OCT find a place in all of this? All the other medical imaging, any medical imaging, you will always look at what's the resolution with which I can image, what's the depth with which I can image. I want to go as deep as possible with the best resolution as possible. Some techniques will give you very good resolution, but very poor depth. some will give you very good depth, not that good resolution, right. So, OCT fits in where it's not very good on depth, but it's better than some other techniques, and again it has a fairly better resolution, okay, and it's completely non-invasive. So, in medical imaging, the OCT is usually done in this wavelength regime in the infrared, and you are creating images one slice at a time, and you can put these slices together and thereby, so you get a 2D slice at a depth within the object of interest, and then you create many 2D slices and thereby you have a 3D image. Okay. Okay. It's really of importance now, because if I can create an image of the eye, you can also, so one thing is you can study the retina. So, if there is any damage to the retina, you can see that. But you could also look at between, so I saw ophthalmology here. So, if you look at the structure of the eye, and clearly I am not going to draw this properly. So, that is the lens of your eye. Actually, you have the cornea, right, and then you have the retina over here. Okay, very bad eye. Clearly, this person needs surgery, but let's take it as this. So, I can either image the retina, or I can use OCT to image this region, right, this region, and thereby measure this angle. And it turns out that angle changes when the pressure in your eye changes, and that's an early warning sign of diabetes. And you know, India's unfortunately got the title of growing diabetes country in the world. You want to make as early a diagnostic as quickly, as simply as possible. So, if you say measuring this angle and seeing the changes of this angle, or seeing it vary from what the average is for most Indians, you can then make quick and non-invasive diagnostic techniques for people. Okay? So, there's a lot of push for this kind of technology. There are two ways of doing OCT, and depending on the time, we will see if we cover both. But the idea of OCT at least will come through the first one. We call this time domain OCT. Okay? So, let us look at this setup. Now, it may not be obvious from this setup, but what you are looking at is a Michelson interferometer. Okay? This particular setup has been built completely with fiber, which is why the arms aren't that stand at 90 degrees to each other, but this is one arm, and it leaves the fiber and it gets expanded and hits a reference mirror, and this mirror has the ability to move, and we will see why that is important, but it is normally incident on the mirror. So, it comes back, re-enters the fiber, and comes. This splitter is nothing but the beam splitter. Okay? The other arm sends light to a sample, and again I will explain why it goes through this little set of optics here and this mirror over here. But basically this is your reference arm and this is your object arm. Again, light reflected off the sample makes its way back and comes here. Now, it comes to the splitter, which means everything that comes through this arm gets split. Half of it goes back this way, half this way, and similarly with this arm. You put a circulator. So, a circulator is an optical device that allows light to flow only in one direction. So, because of this circulator, the light that comes back here does not go back to the broadband source. You do not want it to go back to the source, it will damage the source, but instead you send it here. Okay? So, I actually have two interference signals I am measuring. One is coming from, I have light from, now what did I do? Right? I have light coming from here and it is going here and here, and I have light coming from here and it is going here and here. So, both these arms A and B carry an interference signal. Okay? The property of the splitter though is there is a phase difference between these two signals, and you will see why or how we can use that. I can in principle take only one of these signals and do everything, but there is a slight advantage in using both of them. But one signal alone carries the interference of the reference and the object beam. Okay? Comes to this detector, and then we do some processing, and somehow from this interference pattern we get an image. Okay, let's see how. Important, we don't have a laser here, we have a broadband source. That immediately means, what can you say about poor coherence? So what happens, and don't forget this mirror can move. Okay. Now let's say you set up this experiment such that the mirror, reference mirror is in a fixed position, and you're getting light from one particular plane in your sample, and you have set up this system such that for that plane the optical path length difference is 0. So you have the best I can consider this sample, let's say, just to make it easy, let's say it consists of layers like this. Okay? So I have set up this such that I get reflection, say, I am trying to change this. I have reflection from this layer. Light is reflecting from all the layers. I can't control that. If light is incident on the sample, there is a reflection from the top surface, from every surface or every disturbance within the medium, and from the end of the sample. But I have set up my system such that the path length difference is 0 only for the light reflecting off this one particular layer. It is not 0 for all the other layers, right. So, the signal coming back here is a combination of the light reflected back from every layer in the sample. When the interference happens here, however, it is going to happen only between the light from the reference mirror and the light coming from the sample which is within the coherence length of the source. Does that make sense? What happens to the other light? I have light coming back from layer 1, layer 2, layer 3, layer 4, but I have set it up such that only layer 3 has a 0 path length difference with the reference mirror. So what happens to the reflected light from layer 1, layer 2, layer 5, layer 6, so on? What happens to that? It's just the DC. It doesn't play a role in the cosine term. It's just adding a DC to your signal, right? So that's what this is talking about. This technique is called coherence gating. Although you have light coming back from a large depth, your signal of interest and the signal that you are going to use is gated by the coherence length of the source. You get useful signal only over where the path length difference is matched, and that is going to be decided by the coherence length of your source, right. So, if I were to take a simple Michelson interferometer, let's draw it here, beam splitter, one mirror, another mirror, and I look at on a photodetector here, right. We know now that if these two mirrors are perfectly perpendicular to each other on the photodetector, I am going to get some intensity. Now let us say I move this mirror, one mirror at a particular frequency over a particular distance. If the distance goes beyond the path length difference, so this is L1, let us say this distance, this is L2. So, 2L1 minus 2L2 is the path length difference, assuming everything is in air and neglecting what is happening in the beam splitter. This is a path length difference. Let us say I initially set this up to be 0. My photodetector will have one high value. Now I move mirror M1. It is vibrating at a certain frequency. if it moves such that L1, this difference becomes greater than the coherence length, my intensity, which was a high, will become a 0. And then the mirror moves back again and it's a high. Then it moves further and it becomes a 0. But as it moves, it's moving from the maximum value to the minimum through a range of values. And that is exactly this kind of pattern that you see here. This is a pattern as the path length difference varies, right? So I can use this now to reconstruct, right? Every time the mirror moves to a certain position, I'm changing where the optical path length is matched in the sample. The sample, let me draw just the sample. This is the sample, these are the different layers of the sample. This is the reference mirror, okay? Okay. Now, initially, it's set up, the reference mirror is in a position, so the light coming off here is matched to this position. At this position, the path length difference is 0. I get the maximum intensity for this position. Now, the reference mirror, let's say it moves over here. That means the matching condition is now for this layer. So, if I'm able to track where my mirror is and I see a peak there, I'll say that corresponding location in the sample, there is something happening that's causing light to be reflected. And using this, I'm able to reconstruct my image, okay. So, if you think of this, let's say this was a section of your sample, and to make it simple, we have these thicknesses of uniform thickness. Of course, a real sample tissue will have a lot of scattering centers randomly put. But just to make it easy to understand, we are assuming each layer is a scattering of one kind, right? And if it's very dark, that means it scatters very less light. If it's very bright, it means it scatters a lot of light, okay? So, I'm showing you again only the sample and only the reference mirror on top, right? I am not showing you the rest of the Michelson interferometer. As the mirror moves, you are looking at this interference pattern below. This is the interference pattern below. It's very poor in the beginning because you have very poor reflection in the beginning. It's very bright at this place because you have the maximum reflection at this place. And if you are tracking or able to monitor the movement or the location of the mirror, if you know the refractive index of the sample, you can tell what are the kind of scattering that's happening at different depths, at what depth within the sample, right? Simple concept, right? Working purely by the method of coherence gating. Now, I had said we get the interference signal from two arms of the splitter, and what I am showing you here I can achieve with just one arm of the splitter, because that signal itself is an interference signal. But it turns out if I consider arm 1 as let us call this A, that is coming from one arm, and the other one is this. Because I have access to both these signals, what we do is we take the difference between them. So, you get rid of the DC term completely, you actually use 1A minus 1B, and then you are left with 4 times this signal. So, you have enhanced the term of importance and got rid of the DC term simultaneously, which means you have a better signal to work with. Okay, so that's why we use both the signals. Yeah, you had a question.
I have two questions. One, why is the broadband source required?
Can someone tell why a broadband source is required here? Sorry? that is true that you don't want to send a high power laser through someone's eye, but that's not why. There are limits. Even a laser, as long as it's lower than a certain power, you can send it into the eye. No, the whole idea rests on what? What was the previous slide? Coherence gating. Why? Can you answer then your own question?
I didn't understand the coherence gating part. As in, like, why is it?
Okay, let's say I used a laser. Okay, I used a laser. Now I have a sample. I'm not drawing the full setup. These are the different layers of the sample. This is the reference mirror. Okay. Now I have light reflect of this, and there's light coming off this, there's light coming off this, there's light coming off this, there's light coming off this. If I have a laser, each one of these is an interference signal. They're all strong because a laser has a long coherence length. How do I tell that something happened at this position? I can't tell. I have an interference signal from the top of the sample, from every scattering point within the sample, as well as right at the end of the sample. Because I have poor coherence, what we are saying is, in my sample, here are different layers. Yes, I have reflection from every sample. The same thing, optically the same thing is happening. There's light reflecting everywhere. But I can set it up so that only this beam has zero path length difference with that one. Or forget zero path length difference, only this beam, the path length difference is less than coherence length. So, let's say, let's count each of these beams as L1, L2, L3, L4 and so on, and this is Lm. Let's say the path length to go to the reference mirror and back is Lm, and the path length to go to the first layer and back is L1, to the second layer L2. So, in the case of a laser, Lm minus L1 is always less than the coherence length for, let's say, Li, for any layer. And in this case, Lm minus Li is only equal to 0 or less than Lc for one Li at a time. Does that make sense? Think about it. It's a very simple concept, not that easy to grasp. But do you understand the difference between this condition and this condition? In the first condition, if I use a source with a long coherence length, I am getting an interference signal back from every layer simultaneously. I cannot distinguish layers, and the whole purpose of this imaging is to say something happened here, therefore there's a scatterer here.
But let's say in this case also, if Lm minus L2 is less than coherence length, then Lm minus L1 will also be less than coherence length. Right?
No, it won't be. It won't be. Go and check that out. It won't be. Put numbers and see, it won't be.
In this case, depending on the bandwidth of the broadband source, you will know how many layers you can.
Because, the bandwidth source determines the coherence length, right? The broader the source, the less the coherence length. The less the coherence length, the higher the resolution of your OCT system. Okay? Conventional systems now have like 10 micron. You can get a 10 micron resolution. Because the problem, so you have in this case, I don't know if I have that here. Yeah, so, for example, the source we used, the bandwidth is 74 nanometers. And that means we had a coherence length of 16 microns. Okay? People use up to 100 nanometers, and they may go down in coherence length.
Also, here you wrote IB as IR plus IS minus 2. Why is that case?
That is the condition in the beam splitter. So, this is what happens with the beam splitter. There is a phase shift of pi over here between the two arms. So, we are just making use of that fact. Often we just throw away one arm. We just ensure it doesn't go back to the source. We don't use it. but you can also use it in this case.
Is it the same case in Michelson interferometry also? The glass slab, does this happen? Is there a phase shift?
Yes, it can happen.
Between
Yes.
the one which goes to the screen and the one which goes to the source.
I won't. It depends on the type of splitter that you're using, because these phase changes are happening because of the reflections that are happening. There's a pi phase, so it depends on the beam splitter. But in the fiber splitter, there's definitely a phase change. It depends on the type of beam splitter you're using, but yes, it can happen. So this at least gives you an idea of optical coherence tomography. He asked a very relevant question. It seems like if I say Lm minus L2, if I say this is less than Lc, it seems like Lm minus L1 should be less than Lc2, right? It seems like that, but that's not the case. So go in, I want you to think about this, right? Why is that not the case? Your condition will only be ever satisfied for one small distance, because you're moving your mirror also. Don't forget that. When I say Lm, remember in your experiment, Lm is also moving. Lm is not constant, right? That's why in time domain OCT, the reference mirror moves. So every time I have a new Lm, for that Lm, you are ensuring that the condition is satisfied for one layer in the sample, because I move the mirror to a new position, right? So go think about it. If you have the basic concept, you should be able to reconstruct the working. I do not have time to do the Fourier domain. What the Fourier domain does is, it gets rid of the movement of the reference mirror and says, well, I can just take a Fourier transform of the signal and I can extract the information from there, because it's buried in there, right? So I'll not talk about that, because I want you to get the idea that we've talked about sources with good coherence, but here you want, the poorer the coherence, the better the resolution of the source. And in fact, white light interferometry is used in sensing all the time, because it allows you to measure very small displacements because of the poor coherence length again. You'll only get interference if it's less than the coherence length, and because the coherence length is so small, you can use that to measure very, very small displacements, because you will not get interference unless you're doing that over a very small displacement, okay? So it's not that coherence is required for interference, but we often exploit poor coherence because it gives us better sensitivity, okay? Okay, so I will end with that today.